Okay, so I think we are just 7:59, so we are close to starting point. So people, I mean, those people who are interested in learning more about cryptography, they can actually join this membership of this International Association for Cryptologic Research, and you can find. Maybe I will show you. If you go here, uh, it's a very nice job portal also. So those who are looking for some internship in some company or even higher education like PhD programs or something like that. See, all in cryptography. It's a very active website. So even some PhD positions which are fully funded in this cryptographic area, you can find actually, right? So you can become member. A student member should not be very costly. And you see, there is a list of conferences: Asia Crypt, Eurocrypt, and public key cryptography, and so on. So, those who are really interested in looking at the literature, they can join this International Association for Cryptologic Research, and you can find enough material there. Okay, so now I'm going to give you some very brief introduction about financial cryptography. And because this is the theme of the project, so I guess you can start, because the area is, even the financial cryptography is a very vast area, right? So if you really want to understand or learn a couple of things, you need to start from now, slowly look at the literature, formulate the problem by the deadline, so that you can actually fix a topic. Okay, so there is a story of ships actually. uh, i I think, I'm not sure if you are familiar with this story of ships. It's a very powerful story which has changed the planet forever actually. So there is this bacteria in the ocean, and this bacteria causes different kind of waves in the ocean, like cold wave and hot wave. Okay, and it is because of that, you can, there is a picture which I can show you. If you want to read more about this bacteria, you can always Google it and find more information about this bacteria. So there is a ocean current, cold wave, hot wave. You see these currents are there, right? And the discovery of these currents around 1500 or something was a major discovery for human history, because now people were able to move from one place to the other place, right? And each, I mean, especially in Europe, of course, from India there used to be a lot of business. So for Europe, it is known as Age of Discovery, from 15th century to 17th century. And I think out of this uh, this journey, a lot of interesting things happened. For example, I think you must be knowing that. Uh, have you heard of Mendel experiments in biology, right? So Mendel was actually a padri in that church, right? And when these ships used to come back from different places, and they collect different plants and other things and so on, right? And his job was to analyze and, kind of catalog them and so on. So, that's how he discovered those properties, which is, I would say that it's the first idea about genetics, came from there. And also, because of these ship thing, Charles Darwin wrote that book, Origin of a Species, because he also traveled around the world because of these, ships. So it's a very, very important thing. But where all these ships were going, all of them were coming to India. You see, there are so many East India companies. So you can see that British East India Company you are familiar with, right? Which was started in 1600. Dutch East India Company 1602, and Danish, Portuguese, and other things, French, Swedish, Austrian. All these East India companies were started in Europe, and their job was to come to India and do business, right? Because India has all different kind of things, a lot of diversity in terms of spices and so on. I recently visited Saudi Arabia, so there Bharat means masale. Okay, so that is a thing. Bharat means masale. So if you go to Saudi Arabia, you will find that terminology. So this is something very very interesting thing. So now the Dutch East India Company seems to be the first company, uh, you know, who issued equity certificate. The first founder, the startup culture that you see here, these are the founders. 1602, Dick was the main person, and this was the broker. And those of these three people started, this company, Dutch East India Company, to do business. And now what they used to do, so they were sending these ships to India. And what happens, you gather some money, buy some ships, send it to India. Some of them will be lost. So there is a loss of the business, right? And so the requirement was, okay, they needed more money. So out of 10 ships, maybe 4 will survive or 5 will survive, right? So then they started generating money, and that's how they, in Holland, in Amsterdam, so they actually try to collect money from different people, and so kind of, so that you can diversify, right? So if one ship, if the trip of one ship is successful or two ships are successful, you can make a lot of money once, when the business is successful, right? So that is how the first equity certificate. So this is, I would say that, a very interesting story about the startup culture, okay? And that means the business, okay? And you can find this nice book by Etram, The World's First Stock Exchange. It's a very interesting book to read if you want to know more about these interesting things, And this is the flag of that ship, that company. This is the oldest equity certificate, September 9, 1606. Now, there is another interesting thing about India also. I don't know whether some of you see this picture. So there is a banyan tree or Bargat tree, right? So in Mumbai, so again, couple of traders, they again started putting money in the cotton ships. India was exporting cotton to the Western world, and again the same reason, right? They started, putting money in these cotton ships. So basically, so all this ship business, they started giving shares to those individuals, right? And those shares, they again started selling it to other people, so in the form of these paper shares, that business started. So this thing started in 1606, right? And then after that, many other, because when this concept goes to other places, they also started doing the same thing. So this is a very famous place. Now I think this is an old picture in Bombay, but now the Bombay Stock Exchange, you can see, nearby that place, I have visited Bombay, but I think I have not seen this place anyway. So this is something interesting thing. So in India also, the Bombay Stock Exchange started in around 1850. Now, so when all this thing was going on, everything was fine because there were papers were issued as a share certificate. But then what happened? So that means this thing started in different part of the world, including US and other places. So New York Stock Exchange was started. Again, there was another famous tree there for starting the business. So you can find out. I leave it to you. There is a one tree, and there is an agreement on the name of that tree. That's how the business started actually there. Now, so in US, what happened? In fact, between US and Europe, when these, so ship was the first business thing, what people started. And after that, what happened? Discovery of telegraph happened. So telegraph was a very very important component for so when people started selling shares now, right? Okay, so they've got some share certificate from some company, and then they are selling it to some other person, getting more money, and so on, right? So all that stock exchange beginning started, because the first stock exchange started in Holland, but after that other places also started a stock exchange, right? And then there was all kind of communications going on. Then this telegraph business was used to actually transmit the the value of the share things, right? How much money and so on, so the trading happened because of telegraph. And then in fact, you must be knowing that there is a famous story about how General Electric was formed by Thomas Alva Edison. So he was very poor initially, right? So he used to sleep in New York, just near to this stock exchange, and there was a problem in their telegraph machine in the stock exchange. So then he fixed it, and he got $5,000 in that time, and then he started General Electric, right? So this is the interesting thing. So everything started with ships, and then slowly. So the technology and the basically the business is very very close. For for developing technology, you require business because you require money, and right, and for business you require technology. So both are very very parallel thing, and that happened. And so basically, another important thing came up, what is known as, this electronic trading. Electronic trading means, now, but it's because you see what happens, computers came a bit late, around 70s or 80s. But before that, they used to do most of the business through telegraphs, right? So basically, and for share trading, still they were using paper. So there was a paper crisis that happened actually, it's a very uh, interesting thing that happened in. By the way, this is the list of different stock exchange. You can see that some of them are closed, right, in India. So there was a paperwork crisis in late 1960s. This is something very important because the volume of trading was quite high. Okay, so if volume is quite high, so there is always shortage of paper. You cannot actually. So at many places, for example, in US, they used to close on Wednesday and then open after giving gap of 3-4 days. They again open the stock market because there was an issue. You cannot process so much paper, right? The processing was difficult, and this changed after basically computers were there, to take care of everything. And I think, as you know, that Nasdaq is the fully automated stock market in US, which was based on all this computer business and so on, right? So these kind of thing started. Now, once trading is happening through these computerized things, right? Obviously, different kind of security and other things are needed, right? So this is a kind of beginning of financial cryptography. Of course, some idea about, so after the discovery of internet, some idea about financial cryptography we can trace to David Sham. So in 80s, so this is the paper that he wrote, blind signature for untraceable payments. So he formed this DigiCash in 1989 to create an online currency. But there were a couple of issues, right? I mean, what if somebody will reuse that electronic money again, right? How do we verify? All kind of challenges were there, technical challenges were there, right? And that changed until 2000, which year? 8. Good. So so in 2008, after the discovery of Bitcoin, right? So this is also the term financial cryptography is the first time used by Robert, the Bob Hetikina, in this conference, financial cryptography in 97, right? So basically, you will see that I would say that this area is going to change the future of everything, because even after the discovery of Bitcoin and blockchain technology, it is kind of still evolving and so on, kind of settling down in different directions and so on and so forth. Okay, and so one can ask, what is financial cryptography? Uh, there is a list of these kind of activities: accounting and auditing, programming, system architecture. Of course, cryptographic techniques are there: economics, internet, security, finance, banking, risk, and so on. By the way, I think some of you might be knowing, right? These mathematics and computer science are beautifully applied in different processes. For example, if you have to catch the fraud in the balance sheet, how will you do that? You know, somebody's, kind of manipulating the numbers in the balance sheet. So Satyam, you can caught, right? Satyam scam was there, right? If you remember. So basically, how can you catch that? So what happens? There is a very natural law known as Benford's law. Have you heard of Benford's law? So Benford's law says that whenever you are collecting numbers anywhere in the nature, right? Whether if you start collecting addresses and house number and so on of different places or anything. So or even you know your exam marks, if I start collecting it, you will see that the first digit, so basically any digit D appearing in that data, the probability of appearing it is log of 1 plus 1 by D. That means 1 will appear more often, 2 will appear less often, 3 will appear less, even less, and finally 9 will be the least that will occur, in that data. This is Benford law, beautiful law, and it has wide variety of applications. So people have developed tools, for example, to detect fraud. If the balance sheet is occurring naturally, it will satisfy Benford's law. So if somebody is manipulating the data, so you can caught it actually. You can, it's interesting application, right? So all kind of things are there. By the way, so there is a 7 layer of financial cryptography. This was given by Ian Griggs. So we have cryptography, software engineering is also part of it, rights, accounting, governance, value, and finance, right? So all these major things. Uh, okay, so I think you can read more about it slowly, about this financial thing, financial cryptography. Some terminology that has been used, of course, ATM is one of them, Bitcoin, blockchain, cryptocurrencies, cryptoeconomics, digital currency, okay, cryptocurrency, point of sale, hardware security model, this is a very important one, payment system, smart contracts, economics of security, and bilateral key exchange. Some of these terms are used for different activities, common terms that are used in financial cryptography. So these are some of the areas. I have taken this from this annual conference of financial cryptography. These are some of the areas. I am not saying they are all of them. So you can see that access control, authorization, trust management, right? Anonymity and privacy enhancing technologies. For example, I think if you know, FHE is a very important technology that has been discovered. Have you heard of FHE? FHE means fully homomorphic encryption. That means, your data you can encrypt and then you can apply algorithms on the top of it on the encrypted data. That is possible. Okay. So it's a beautiful thing, right? So everything is encrypted. So your data is encrypted in cloud or whatever, and you can do, so you can do all kind of machine learning or every other kind of thing on that encrypted data. So that is something really very interesting thing to look at, right? So you see there is also fraud detection, forensics, electronic crime. Of course, I'm not going to read all of them, but you can look at it, right? So all kind of things are there in the financial cryptography. So I I would suggest that you can maybe search each particular area and try to find out something that you are going to do for the second part of the thing, right? Because I've asked you to submit a PPT in this area, right? You just pick up one and start preparing now, because that submission will be due in sometime in February, right? Okay. So no, so sorry, after exam in March, 8th March is the deadline, right? So you have enough time by the time. If you start now learning about one particular area, whichever is interest to you, you can then, learn more about it. So this is again, there is an International Financial Cryptography Association. You can become member here also if you're really excited about financial cryptography, right? So first of all, if you are interested in cryptography, you should become member of International Association for Cryptologic Research. And if you are more interested, then you can join this financial cryptography conference. And I think there are some interesting things there. Uh, I think one submission is something around 12th of June. So if you want to, and there are two kind of opportunities available in the conference. One is that you can pitch something in the financial cryptography domain, right? You can pitch off something if you want to start a company. So some of you who are interested in starting a company, you can pitch for something in that area. Second, you can write a paper if you want. I mean, that opportunity is also available. Those who want to go for higher studies, that could be interesting thing, right? Or otherwise also for job market also, this is very hot. Financial cryptography is very hot, right? Because it covers both the things, finance and cryptography and security. This conference, 2023, will happen in May. So I think I'm not sure the submission deadline. One has to check what is the submission deadline for this. Okay. So this is all about financial cryptography. So of course, where is your startup that you can think of? By the way, who is Satoshi Nakamoto? Do you know? Bitcoin? But nobody knows who is this person, right? You know that? People are trying to find out who is this person. So I think he worked till 2010. I mean, he or a group of people, nobody knows. A single person. People are trying to look at his code, what he has written, and trying to see, okay, maybe he's Spanish or Australian or whatever, may not be Japanese. So all kind of, people are trying to analyze even that thing, right? Why he is hiding? One knows, right? So I mean, something interesting in mystery, right? So it's something, if you can find out, you can write a blog about it anyway. So I think people are even analyzing the logs that he's submitting, right? About I think that was till 2010 and after. In fact, some people interacted with him online, but they don't know the location. So something, it's a very interesting thing where he's. Anyway, so that's all about some basics of. I think this seminal papers, I will talk about it later on. Now, okay, so any question up to this point? You can ask me. If you query me, then more things will come, right? You don't ask, it is one-way communication, and that is a good thing. Physical, online, there is not much interaction. Anyway, so now I think I am going to start classical cryptography first. As I mentioned, this is the broader classification. Classical cryptography means the ciphers and their analysis, private key cryptography, public key cryptography, and then protocol level, right? So to start with classical cryptography, again, uh, I will take you to your 2021 batch, right? 2020 batch, okay. So you may be remembering first or second or third lecture on discrete math. भूल गए सब. So, again, so remember, data is always a packet, and packet lies is some field. What is field? Field is a set, or so normally what is football field? Where you can play with footballs, right? Cricket field where you can play with crickets, and data field is normally field, where you can play with all the addition, subtraction, multiplication, division, all the four operations. That is a field. And then we are going to talk about finite field with finite number of elements. Okay. So the popular example is integer modulo 2, right? So we know that integer modulo 2 is a field, integer modulo 3 is a field, integer modulo 4 is not a field, integer modulo 5 is a field, integer modulo 6 not a field, right? So essentially integer modulo n is a field if and only if n is a prime number, right? So that is the basic result you may be recalling. So I'll just give some overview because we need to catch up from there. Okay. What is this modular arithmetic? So integer modulo m, so set of numbers 0, 1, 2, 3 up to m minus 1, and the addition operation is addition modulo m, right? And multiplication modulo m, right? So this is a ring. How many of you are from maths and computing background? Okay. So are you aware of these concepts? Okay. But may not be about finite field, right? Anyway, we'll see. So this is a ring. For m is equal to 2, we have the binary field, right? Z2. So what is field? Field means a set where we can do all the 4 operations: addition, subtraction, multiplication, division. Well-known examples are field of rational numbers, field of real numbers, field of complex numbers. So these 3 fields are examples of infinite fields, right? Because the number of elements are infinite. Q, R, C are 3 examples of infinite fields, right? Then for Z2, I can make these tables, and these tables are very easy for you to understand, grasp the whole idea. So if you make this table plus 2, 0, 1, 0, 1, so I can say that 0 plus 0 is 0, 0 plus 1 is 1 plus 0 is 1, and 1 plus 1 is 0. So this is addition. With respect to multiplication, we have 0 into 0 is 0, 0 into 1 is 0, 1 into 0 is 0, and 1 into 1 is 1. Now this is a field. With respect to addition, everything looks okay because everything is appearing exactly once. But here I would like to check that every non-zero element in the set has a inverse. So we know that 1 is the only non-zero element, and 1 into 1 is equal to 1. That means 1 is self-invertive, right? So every element has the inverse. Every non-zero element has inverse, and there is one non-zero element which has inverse, right? So this is Z2. Then we can go to Z3. Integer modulo 3, we can make tables similarly, and we can check that here again every non-zero element has a inverse. So what is the inverse of 1? Can you tell? 1, because 1 into 1 is 1. What is the inverse of 2? 2, because 2 into 2 is 1. Since 2 into 2 is equal to 1, so 2 is equal to 1 by 2, right? I mean, that is something. So basically 2 is 1 by 2 is equal to 2, because 2 inverse is 2, right? Just to confuse, I mean, this is very nice thing, right? So this is about binary field. This is known as ternary field. Binary field, ternary field, right? We can go little bit further. Any question about the at this slide? Please do ask me. Any question, or everything is clear? If you understand everything, no question. If you don't understand anything, then no question, right? So what is the case? The first or the later? First. Okay, good. Now we go to integer modulo m. Now we know that Z4 is my favorite because I did my PhD on Z4 actually, I can do entire linear algebra on Z4 in a different way. Okay. So all your concepts of linear algebra that you have been till now understanding will change. Anyway, so Z4 is a ring, and now you can see that table with respect to addition is 0, 1, 2, 3. You can add everything and get the table. Why it is not a field? Because you see, I'm checking whether every element has an inverse. So 0 has, non-zero element should have an inverse in Z4. So if you look at 1, 1 into 1 is 1. So 1 has inverse, no problem. 2 has no inverse because 2 into 2 is equal to 0. Right? So I cannot multiply 2 with any other number in the set such that I should get 1. There is no such number, right? X such that 2 into x is equal to 1. Right? This is not possible. So 2 is non-invertible. 3 has the inverse because 3 into 3 is equal to 1. Right? So that is fine. So one question one can ask, if A is a non-zero element in integer modulo m, so inverse of A will exist if and only if GCD of A and M is 1. So can you prove this? Tea time problem, right? You require a good cup of tea or coffee in the evening today and do this exercise, right? So an element A in Zm will have inverse if and only if GCD of A and M is 1. This is a, see, so please do this problem because I may ask this in a quiz or in an exam or anywhere. That is one reason. Second reason, obviously you will understand something, right? So it's something not very difficult, okay? Now we know that if M is a prime number, Zp, so every will element, because in Gp, so GCD of A and P is 1 for every non-zero A in Zp, right? So that means every element has an inverse if M is a prime number, right? That is true by default. So this is an interesting result actually that I would like you to prove. Okay, that A in Zm has an inverse if and only if GCD of A and M is 1. Of course, so how will you prove it? Any idea? I mean, you can start with this side, maybe suppose GCD of A and M is 1, try to show that there exists a element B such that A into B is equal to 1, right? That kind of thing. I mean, if GCD of A and M is 1, there exist integers uh, P and Q such that AP plus MQ is equal to 1. Remember a elementary number theory result? And then you use that result to find a inverse, which is straightforward. This way is straightforward. Similarly, you can show the other way, right? So I'll leave it to you as a tea time problem for this. Okay. Now, another interesting thing for Z5, let us see Z5, M is equal to 5. So we have, you know, we can make table and so on. Now you see that what is 2 by 3 in Z5? 2 by 3 is 5, right? 2 by 3 is 5. Why? Because 2 by 3 is equal to 2 into 3 inverse. 3 inverse is 2 modulo 5. And so 2 into 2 is 4. So 2 by 3 is 4. It's a bit different, right? What about the value of 1 by 2? In integer modulo 5, 1 by 2. That means I'm asking inverse of 2, 3. Got it? So I hope you understand. Till 12th or whatever, yeah, I think even some courses here, you will never encounter these kind of things, right? These are the beautiful things because you can see interesting stuff. Anyway, so now I'm going to list some of the properties. So Zm is a ring. So ring is basically a algebraic structure which is a little bit generalized to the field, right? It's a general thing. So in field, whenever A into B is equal to 0, one of them has to be 0 in field. This is the property of the field. But in the ring, that may not be true. There are presence of 0 divisors. So neither A is 0 nor B is 0, but their product is 0. For example, in Z4, 2 is such element because 2 into 2 is equal to 0, right? So this is a very important thing. Anyway, so if you take two elements A and B in Zm, their addition is in Zm, right? If you take two elements, we have the commutative with respect to addition, right? So normally they teach ring like this. I don't like this, but anyway, these are the properties. I would say that, right? But you can understand the definition. Anyway, so if A, B, C are in Zm, so A plus B plus C is equal to A plus B plus C, right? That kind of property is there. There exists a additive identity in Zm such that for any A in Zm, A plus 0 is equal to 0 plus A is equal to A. Additive identity, right? 0 is there, very important. There exists additive inverse for any A. So A plus M minus A is equal to M minus A plus A is equal to 0, right? Because modulo M, that will be 0, right? Anyway, okay. If A and B are in Zm, their product is in Zm. If A and B are in Zm, then AB is equal to BA, fine. If ABC in Zm, then A into B times C is equal to A times B into C. There exists a multiplicative identity 1 in Zm for any A in Zm. Whether this will happen every time? Not, right? Because Zm is ring. If M is equal to prime, then this will happen every time. Okay? Otherwise not. And the distributive property and so on, that is there anyway. Now, there is a one beautiful thing, what is known as Euler-Toscan function. I don't know, have you heard of this? Very beautiful function, right? Euler-Toscan function, which is kind of counting, right? So now we focus on Z26. Why we are focusing on Z26? Alphabet, English alphabet. You know that now they are 26, earlier they were 24, right? So now this 26 is equal to 2 into 13, right? So it's obviously product of two prime numbers. Now, if A is a non-zero element in Zm, such that its inverse exists, right? I mean this Z26 I am talking about. So M I am taking Z26. So how many times? So basically, GCD of A and M is 1, right? If GCD of A and M is 1, then inverse will exist, right? We know that, right? So how many such elements will be there, which will be invertible in Zm? No, no. So basically, I'm saying in Zm, integer modulo M, I'm asking general question. In integer modulo M, how many elements A are there which will have inverse? So that means how many times is GCD is 1? I am asking this question, right? GCD of A and M is 1. How many times? You can count, right? And that turns out that it is nothing but the Euler-Tauschen function. So phi of 26, phi of M is phi of 2 into phi of 13 because 2 and 13 are prime numbers, right? So this Euler-Tauschen function, you know that it's a multiplicative function. So if GCD of M and N is 1, then phi of M into N, phi of M into N is equal to phi of M into phi of N. Okay. So that means phi of 26 is equal to phi of 2 into phi of 13. 2 is a prime number, so this value will be 1. Phi of 13 will be 12. Phi of P is equal to P minus 1. Right. So this is whole thing is how much? 12. So there will be 12 elements in Z26 which will have inverse, right? So one can list whether 0 or because 0 we can avoid. 1 will have inverse, right? 2 will have inverse? No. 3 will have inverse? Yes. You're just counting the GCD. 4 will not have inverse, 5 will have inverse, 6 will not have inverse, 7 will have, 9 will have, 11 will have, then 15, 17, 19, 23 and 25. There are 12 elements which will have inverse because they have GCD 1 with 26, right? Got it? M is equal to 26. There are 12 elements, okay? No, so phi of 39 you need to compute. Basically, what is the factorization of 39? 3 of 13, right? So it is phi of 3 is 2 times 12, 24. So you just verify basically if you are having a doubt whether they are those many. Basically, formula is that, right? In check, okay. Anyway, so basically, so this is something very interesting actually. In fact, one can use this fact to show that if AX is congruent to B mod M, so solution will exist when? How do we solve this for X actually, This is something interesting thing, okay? How do we solve for X? Obviously, if inverse exists, you can multiply with inverse on both sides and you can get the solution, right? So obviously, if inverse exists, you can solve that. I mean, of course, there are some calculations, but over Zm, I think over Zm, there are very interesting things that are possible. For example, if you take the equation ax square plus bx plus c is equal to 0, you know what is that equation? Sheetar formula, right? And a is not equal to 0. So if ABC belongs to Z2, how will you solve it? Or Z3 or Z4? Whether the Sheetar formula will work? That is one question. Anyway, let me show you some of the stuff here. In fact, I'm going to answer that. Now we know that finite fields. Is there a field with one number of element? No, because 0 and 1 at least required, right? Additive identity, multiplicative identity. What about, 2? Yes, Z2 is there. 3, Z3 is there. 4, Z4 is not a field. 5, yes. Z6 not a field, right? And so on. So the question is, can we construct a field with 4 number of elements, even if Z4 is not a field, right? So question is, how do we do that? So the idea is really very simple and very fundamental, very basic, and which is used to really construct the whole finite field business. So let me show you some stuff here. By the way, this is used in elliptical cryptography and AES, all these standards. They are using this finite field business. It's a very important thing anyway. So now we know that if you look at real numbers are, and we know that there are, if I take a equation, I can solve in reals, right? Normally. But if I take equation x square plus 1 is equal to 0 on reals, is there any solution in the reals? No, because there will be no real. It's imaginary one, you know that, right? Square root of -1 is a solution. So that means what we are doing here, this equation has no root in reals. So if I write down square root of -1 as I, okay, and we consider C, how we construct field of complex numbers. C is equal to A plus IB such that A and B are R and I square plus 1 is equal to 0. Right? So there is a root of the equation x square plus 1 is equal to 0, which is not in the ground field R, but maybe outside R, which is in C. Okay. So C is formed like A plus IB, where A and B are reals, right? So basically, we also write it like R attached with I. We have attached root I to the reals, and we get the complex field or the complex plane. You are familiar with complex plane, right? So this machinery is a very basic way of constructing larger fields from the ground field. By taking a polynomial, this approach is very basic. Taking a polynomial which is irreducible over the ground field, means which has no root over the ground field, take the root of it, attach it to the ground field, and you get the bigger one. Like this. The mechanism is like A plus IB, where A and B are reals. And right. So now, if I look at this ground field Z2, which is having only two elements, 0 and 1, this is the smallest field that we have with two number of elements. If I take 0 comma 1, so then I need to consider this equation ax square plus bx plus c is equal to 0, where a is not equal to 0 and abc belongs to Z2. Then how do we solve it? Good thing is here, since a, b, c are binary, 0 or 1, right, except a is not equal to 0, I can write down how many equations will be there. 4. X square plus bx plus c will be the general thing, and then b has two choices, c has two choices, total 4. So I can write x square plus x equal to 0, x square plus 1 is equal to 0, x square is equal to 0, and x square plus x plus 1 is equal to 0. All 4 equations. Now, whether this equation has a root over Z2, x square plus x, yes, this has a root, x equal to 0, right? Or also x equal to 1 is also a root here, right? -1 is same thing as +1 modulo 2, right? So this is not going to work for us because I am looking for an equation which has no root in the ground field, right? What about x square plus 1 is equal to 0? X equal to 1 is a root, so this is also not a proper equation. What about x square equal to 0? X equal to 0 is a root, so that is also not possible. So what we are left with, x square plus x plus 1 is equal to 0. Now x square plus x plus 1 is equal to 0. Is there any root if I substitute x equal to 0? No. X equal to 1, 1 plus 1 plus 1 is 1. This is also not a solution. So all these elements of the ground field are not a solution. So this is the irreducible polynomial. So there in the reals to complex, I have taken equation x square plus 1 is equal to 0. Here I can take the equation x square plus x plus 1 is equal to 0 for the construction of field with 4 number of elements. So how do we do the construction? So we call, suppose alpha is the root of x square plus x plus 1 is equal to 0. So if alpha is the root of this, that means alpha square plus alpha plus 1 is equal to 0. Just like that, we call I is the root of x square plus 1. Here I am calling alpha is the root of x square plus x plus 1 is equal to 0, right? Any question at this point before going further? Clear? Alpha is a root here. Now, So we construct the field with 4 number of elements as a plus alpha b such that a and b are in Z2 and alpha square plus alpha plus 1 is equal to 0. That is our definition. I have naturally extended the definition just from real to complex. I did same thing here. So now if I actually look at a plus a and b in Z2, so you see that what are the 4 elements? 0, 1, 1 plus alpha and alpha, right? These are the 4 possibilities. When we choose A is either 0 or 1 and B is either 0 or 1. We have 4 elements. We'll get these 4 elements. Now, we know that 1 plus alpha is same thing as alpha square, right? Because alpha square plus alpha plus 1 is equal to 0. So that means alpha is equal to alpha square is equal to minus of 1 plus alpha. But minus is same thing as plus 1 because minus 1 plus 1 is 1 plus 1 is 0. So you are getting alpha square is equal to 1 plus alpha, right? ये पढ़ चुके हो पहले डिस्क्रीट मैथ में, अभी तो भूल गए होगे. So I'm just recollecting the fact. इसीलिए मैं लिख नहीं रहा हूँ. Everything is written already. I'm just recalling. Okay. Also note that alpha cube is equal to alpha into alpha square. Alpha square is equal to 1 plus alpha. So it is alpha into alpha plus 1, which is alpha square plus alpha. Alpha square plus alpha is 1 because alpha square plus alpha plus 1 is equal to 0. So alpha cube is equal to 1. Now it looks like it is a cube root of unity, right? But is it really a cube root of unity? Because see in the reals or complex what happens? I mean, this is also a cube root of unity, but not over the, because in reals you may be remembering omega, they use the notation omega, right? Omega square plus omega plus 1 is equal to 0. So omega is cube root of unity, and then you can find the formula in some complex number, right? But here there is no complex number. So don't confuse that here. That is separate, this is separate. That was over infinite fields. This is over finite fields. And finite fields are beautiful. You can play, right? You will observe interesting things on over finite fields. This is the basis of your all computer science, finite field, very basic thing. And many people find it difficult to absorb the material. So if you want to absorb the material, you have to just enjoy it, right? With a cup of coffee. Okay. So should we finish it? Oh, so this is slow actually. Anyway, so again, we will come back again here. We'll do the tables here and then we'll go back. Okay. So I think probably another lecture will be on this and then we'll start ciphers. Okay. At least 2 basic things are required.